Hello there guys, welcome back to another epic inexorable maths video. In this video I'm going to answer a question that some people have asked me in the past. And that is, when you do integration by parts, why do you not need to do a plus c on v? So when you integrate dv dx, why is there no plus c? So let me explain exactly what I mean. Imagine that we were doing a fairly straightforward integration by parts question. Something like the integral of x times e to the x. Okay, well how would you do this? Well, you would let u equal x, you would let dv dx equal e to the x, you would find du dx to be the number 1, and you would find v to be e to the x, right? Sounds good so far. But the question is, why is it not e to the x plus c? Because that is the integral of e to the x. It's not e to the x, it's e to the x plus c. So why is this not here when you do all your working out? Surely you're doing something wrong, because this plus c needs to be there. It must be. Don't forget the plus c. So many people tell it to me. Everyone, my teacher says it, everyone says it, everyone, you go on a YouTube video, don't forget plus c, don't forget plus c. There's a plus c right there, but you don't do it. Why? Well, I'm going to try and answer the question. So basically, in one sentence, you don't need a plus c because everything cancels out by the end of the question. The plus c cancels out. But I want to actually show you. So I'm going to show you with this question, and then I'm going to show you in the general case where I replace v with v plus c, and I'm going to show you that everything cancels out. So with this question, let's finish it off and see, no pun intended, what happens. So we have that the integral of x e to the x dx is going to be u times our new version of v, which is e to the x plus c. That's going to be x times e to the x plus c. Take away du dx times e to the x plus c, the integral of that. So we're going to have e to the x plus c times the number 1. So I'm not going to write it because it's just the number 1, dx. Okay, right, and maybe you can already see what happens. So expanding this out, we have x e to the x plus cx minus, and what's this integral going to be, guys? Well, e to the x integrates to just e to the x. So we're going to have a minus e to the x here. And c is a constant, so it's going to integrate to cx. And remember, we're taking this all away, so it's going to be a negative there, so minus cx. And we want another arbitrary constant of integration, but just for simplicity, I'm not going to use the letter c again, because that would be confusing. So I'm going to add a different letter of the alphabet, but it doesn't mean that it's any different. So I'm going to do a plus d. It doesn't mean anything. It's another arbitrary constant of integration, okay? I just don't want to write plus c because there is already some c's lying around, but technically I could have, right? It's just that c and d aren't necessarily the same number. Anyway, look at what happens, guys. Cx minus cx, goodbye, farewell. And then what do we have? We have x e to the x minus e to the x plus an arbitrary constant of integration that I've called d, that you could call whatever you want, and just because I want to make it crystal clear, I will call it c plus c. But it's not the same c as up here, okay? But it gives you this, it's an arbitrary constant of integration. So you do get, if you know what the integral of x e to the x is with integration by parts, you may recognize this. This is what it integrates to if you didn't have a plus c there. Please just take my word for it if you don't know that. I'm not going to do all the working out for you guys, but this is what, you can try it yourself, this is what x e to the x differentiates to with integration by parts, even if there isn't a c there. Now, what I shall do right now is I'm going to just go, because you might say, oh, that's a coincidence though. You might say, oh, that's just one example, you've not proven anything. I'm going to go straight in to the actual formula, replacing all of the v's with v plus c's, and I will show you that it will always cancel out, regardless of what v is. So we have the normal formula for integration by parts, but I'm going to replace the v's with v plus c's, okay? Just like this, okay. So basically this is, if I was using the formula with some arbitrary functions, you know, u and dv dx, and then when I integrated dv dx, I just chose to write it as v plus c instead of v. This is what you would get. Now what I will show you is that this is going to simplify back to this, okay? That's all it's going to be. So this is u times v plus u times c minus, and this is a little bit complicated, so I'm going to do this in a couple of steps. The integral, I'm going to expand this out, of v times du dx with respect to x minus the integral of c times du dx with respect to x. Hopefully you guys are happy with that. I've expanded the brackets out and then I turn it into two integrals and I distributed the negative sign. That's why there's two negative signs, one there and one there. That's why they're there. Hopefully that makes sense. And then we can do something with this integral here. So this integral I'm leaving. I'm just going to keep it as the integral of v times du dx with respect to x. That's fine. I don't want to touch that. But this integral is going to simplify very, very nicely because we're integrating the derivative of u with respect to x with respect to x. So du dx integrated is just u, and it's being multiplied by c. So this is going to be minus c times u. And once again, I'm going to add a constant of integration, and as to not be confusing, I'm going to call it plus d. But it's just an arbitrary constant of integration. It could be a plus c if you want. I'm going to turn it into a plus c at the end, but for now it's just plus d because this c and this d are not necessarily the same number. Okay, and then finally, look at what happens. We have a u times c, and I've written it the other way around, but this is still a u times c, cu, uc, doesn't matter. So these cancel out. And what do we have, guys? We have minus the integral, so uv minus the integral of v times du dx with respect to x plus d, where d is some arbitrary constant of integration. And so what we have here is if you include a plus c in your v, you will get the exact same thing, and it's just going to differ by some arbitrary constant d. But the thing is it doesn't matter that it's differing by a constant, because this, when you integrate this will also have an arbitrary constant anyway. So what you could have, hypothetically, is that this integral here, when you actually do this, this becomes, you know, blah, 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 whatever function that you like. This is a function. And the constant of integration could be, I don't know, it could be something like some constant minus another constant. I'll just choose what c is so that I can have c minus d right there. It doesn't matter. And then I'm just adding d on the end, right? And so there's ways in which you can think of it as having the exact same arbitrary constant or, you know, equivalent. So you have uv minus a bunch of stuff plus c again. Okay, don't worry too much about this end bit if you're not really happy with that. But the point is you have a plus d there. You do this, you have a plus c. These things don't matter. It doesn't matter if you integrate a function and you get a different arbitrary constant to if you use a different method to integrate. There's times where you can integrate functions in two different methods and you will actually get different arbitrary constants out of the end. And that's really not a problem. So actually, in one of the next videos, I'm going to show you an example where you can integrate one function, sine x times cos x, in 4 different ways, and almost all of those ways will give you a different arbitrary constant out the end. But they're all correct. So don't worry that there's a different arbitrary constant out the front. It makes absolutely no difference. And it's not even noticeable when you actually do a question. So hopefully that kind of answers your question, because you can see in this step right here that we do have the exact same formula, only differing by the constant d. And again, D doesn't even necessarily need to be there because when you integrate this, you'll have another arbitrary constant. So it's just one arbitrary constant times another arbitrary constant, which just means you have one arbitrary constant once again. Quite a lot of arbitrary constants. So hopefully that kind of answered your questions, guys. I highly appreciate you watching as always. And I will see you in the next video. Cheers.